so it's officially 3:01. So hopefully it looks like the flow of attendees is still rising, but they'll get in and going. So welcome everybody to the Gatlinburg Statistics and Methodology pre-conference. My name is Kristen Farmer, and Drew and I will be kind of hosting our guest here for you. We've been holding this pre-conference session for the past few years, and our goal is to provide some targeted training in all things data. So in the past few sessions, we've covered some analytic approaches and data management. And today we turn to one of the most important methods we use to understand our data, which is visualization. So we are lucky and excited to be joined by Dr. Sadeghi, who is a data scientist in the section of clinical and computational psychiatry at NIMH. As you can probably guess from that name, her section uses fMRI and MEG modalities to study the pathophysiology, treatment, and prevention of childhood onset mental illness. And during her career, Dr. Sadeghi has worked in the development of advanced statistical and machine learning techniques to discover biomarkers related to neurological and psychiatric disorder. And of particular interest to us here at Gatlinburg is perhaps some of her work, which has been in Mobius syndrome, Down syndrome, and autism. So we are really excited to welcome Dr. Sadeghi to review the principles of data visualization, which of course is an essential tool in exploration and scientific discovery for data sets of all sizes. And so just a reminder that with such a large group, we are going to ask you to please direct all questions to the Q&A tab, which is different from the chat tab. So to the Q&A tab, and we will take all of those at the end. And so without further ado, I will turn it over to Dr. Sadeghi. Welcome.
Thank you, Kristen. Thanks everybody for joining. So I get started. Okay, just a quick overview of the talk. So I will briefly talk about some visualization principles. And more specifically, then I will talk about ggplot2 package in R and give some specific examples and hopefully that you can use in your research. Then also I will show some examples from my own research that I'm currently doing, which is actually about COVID effects on healthy and depressed adolescents. So this is ongoing work, it is not published yet. So just some of the data analysis that I'm doing in our project. I will show. And then at the end, I will also show some brain imaging data since I've done a lot of work in that area and I find it very interesting. So why data visualization? I think a lot of you already know the answer to that question, but some of the main areas that I think it covers, it's communication. So if you want to tell somebody about something, it's so much easier to have a graph or have a plot or just a nice visualization to tell a story and to be able to communicate what we want to say effectively. Another area is exploratory data analysis for scientific discovery. It's really nice to look at the data and try to see if we find any patterns. Do things stand out? Maybe we see some things that we were not expecting. So all of that is very useful with data visualization. Also, every step of the process, even like before you get to the results, just when you gather your data, it's very important to look at it. Maybe there was an error in the way we gather the data, and maybe you find an error. So it's really important to see it in every step, essentially. So here, it's a classic graphic visualization that they use in a lot of visualization classes. I actually saw this first about probably 10 years ago in my visualization class, and I really found it interesting. It's about Minard. So Minard is the person who basically did the visualization. It's about Napoleon's 1812 march. So at that point, Napoleon was getting very powerful. He wanted to go and invade Russia, and he gathered a force of 400,000 people, so the 400 troops, to go invade Russia. And here you can see this is where they start, and this is Moscow here. So Russian army was a lot, they had less soldiers. So as the French army would advance, Russians would retreat, but they would burn everything that was in that area. So the French army was left with no supplies. And as we go, they've made further along the path, they basically got into the fall and winter, the temperatures dropped. So they lost a lot of their soldiers due to lack of supplies, weather, the conditions, everything. So you can see here, they start with 400,000 people. And as they go, this thing gets thinner and thinner and thinner. By the time we get to Moscow, there were like 100,000 people. At that point, they're like, okay, we cannot invade Russia. So they decide to actually retreat back. And you can see even on the way back, they keep losing more people. And here you can see how much they lost more because there was a river, it was cold. So they lost more people. Here you can see the same thing. So this graph shows very nicely, like kind of tells a story about what happened. It has a geographical location, has like rivers on it. It shows what happens going to Russia, what happens coming back, how the troops changes, what's the temperature, what's the latitude, what's the altitude. So it has so many dimensions that brings it all together to tell a story. So this was just like a nice visualization that I want to show you. But also our brain is just so much, when it looks at graphs and plots, it works so much faster than you try to read a paragraph or look at a bunch of numbers and try to figure out what's going on. For example, here, if I ask you how many times the word data appears in this paragraph, you have to read the whole thing and then count. But then if I just color coded, it's so much easier to see that. Sorry, do you still see the whole slides, or did I come out?
No, I went to your
Okay, sorry, I'll go back to the present review.
There it goes.
Yeah, sorry. So it's just our brains are also wired to look at pictures and we figure out things a lot faster and otherwise just going through a bunch of numbers. Speaking of numbers, but now I'm going to show you some numbers. This is also another famous example by Anscombe. He was an English statistician who wanted to also prove the point, even though he was a statistician and did a lot of stats, but also wanted to prove the point, the importance of plotting data and visualizing. So he created 4 data sets, as you can see here. I've shown the 4 data sets. And each of these data sets have the same mean of X, variance of X, mean of Y, and variance of Y, and correlation. So if I calculate all these 4 have the same basic statistics essentially. But then if you plot them, they look very different. So if you just look at the number and you do some basic statistics, you would think it's like the same kind of data. But you see this is quite different. And if you would have not looked at it and just did a linear model and then just looked at the coefficients, it probably would not be the best thing to do. So for the first one, this is actually not a bad thing to do. It's like a linear relationship. You can fit a linear model. But here you can see it's not nonlinear, it's the nonlinear relationship. And this is not a good way to do the analysis here. And this one, you can see there's like an outlier point here. So you should do a robust regression. Here, all the points are gathered in this point, and this one point will have a lot of effect on this, how this line would be. Like if it would be down here, you would get totally different trend. So he just want to point out that how important it is to look at your data, even though you may get same basic statistics, but the data may tell you a different story. Here is another example trying to show as X increases, the synthetic example that I created, as X increases, Y decreases. But if you look at this, if the data was color coded and these are different individuals, it's actually increasing trend. So again, you see a different pattern and you can just highlight it by color coding it so that it's different individuals. Here's another example that I used when I was looking at the brain images. It's actually RDs, the radial diffusivity is a measure from diffusion MRI. And this is early brain development. So it's like basically you image babies, and as they age, this measure goes down significantly. However, if we look at it individually, it's even still going down, but not at the same rate that this was going. So again, it's just really important to look at and also plot them correctly and do analysis correctly. So just going through some basic foundational principles on visualization. So there is different visual encoding channels that we can use to plot data and to show and what we want to show our audience. So we can use color, we can use density, we have volume, area, angles, slope, length, and position. And this is also from a classic paper that they did multiple studies and tried to do different plots using different kind of forms of the encoding channels and to see which one people would basically grasp the idea faster, how accurate they are, and so on, and to find out what's the best way to use to show data essentially. And they figured out that there's a gradient here. So color and density, you might be surprised, and actually very hard to interpret, as the positions and length is easier. So it was like less accurate on this side and more accurate on this side. So color, I mean, I showed it earlier, is good for grouping, but if you want to look for pattern for specific individual, like we won't color them different for each of their time point. We won't use a different color. But again, it's good for grouping structure. Position is better if you want to just show like a scatter plot or something like that. It's a lot better and quicker for people to see it. And I'll show some examples later on. Another thing is use a pie chart or bar plot. If I ask you here if group B has more, is bigger, or group C, it's very hard to say here. They look about the same. At least to me, it looks about the same. However, if I just put in a bar plot, it's very easy to look at it and you can clearly see which one is higher, which one has more people in it. So a lot of people actually in visualization don't like pie charts because it's so hard to detect these small differences. And here it's not even that small, but it's very hard to see. So the position length of these bars, it makes it easier for us to see. So like now diving down to R, I want to show like some specific examples, hopefully, and that you can use your own research. And I mainly code in R, and I'm going to show examples in R, but also why R. We can use Excel, for example, or you can use more other programming languages like Python, or do more complex things with interactive web apps. So R is, I think most of you know, is a open source, is free, and it works in multiple operating systems. It also has a big user community that they keep adding to it, and we have a lot of packages available. This also was invented by statisticians, so because they wanted to do some interactive plotting and to look at their data. So it's very good for exploratory data analysis. And in particular, we will talk about ggplot2 package, which is powerful package for creating plots, and because it works, GG actually stands for grammar of graphics, and it works by, it kind of has an intuitive syntax once you grasp it, and you can keep adding layers, so you can create more complex plots, but also you can just do simple ones pretty quickly. So just going over like basic of ggplot. So it works based on I would say it has three main parts. One is you define your data, and you will have to have the observations in rows. So each row is a different observation, and then each column is a different variable that you have. So we have variable f and a here. And we define a geom. So geom is the type of plot, actually. It can be a scatter plot, bar plot, histogram, and so on. And you have a mapping that you want basically say, what is your X, what is your Y? So here you say you want the X to be F column, and then your Y be A column. And you also define a coordinate system. So typically for most example, at least most of the ones that I work with, you just use Cartesian coordinate, which is the default. So usually don't do much with this. And then you basically get your plot with these two items here. You can also have, there's different encodings that you can do. You can define a color or size. So you can see each of these points have different size and color. And by the way, this is from ggplot cheat sheet that's available in our studio. I highly recommend it. So this might to go to when I don't know a specific syntax, it's very quick to look at that. So here I'm going to go through specific examples about US gun murders in 2010. This was an example that is from Rafael Irizzi. And here's a link to the source. So it's a very good step-by-step way of looking at the data and how we can create something like this plot. So first thing you will do, install. So this data came from this package, Data Science Labs. So you install the package and then the library and the data. So you work with this data. So you're loading essentially this data set. And that was like the first step that we wanted for our to plot something. I'm just looking at the top rows of this. So head, it basically shows the top rows of this data set. So you can see it has the name of the states, the abbreviation for each state, the region, population, and total murders. Actually, this is the murder numbers. So here are our variable names. So each column is different variable. And then we have each row that are different observation. So the next thing is looking at the geom, so the geometry essentially. So there's also other layers like statistics or labels. And as I mentioned, you can just keep adding to the plot that you have by creating additional layers. And there's different geoms available. So the geom point is the scatter plot, geom bar is a bar plot, geom histogram. For histogram, there's many more different geoms so that you can play with it and see what each one of it does. It's very intuitive. I mean, most of them start with geom, and then as you can see, the names are kind of what you expect they would do. So let's try to do some plotting. So if I call the ggplot and just pass it in the data, I just get big empty gray box because I haven't said, okay, what kind of plot I want, which is defined by this geom function here. So we want a scatter plot, which is defined by geom point. So if you do question mark geom point, basically gives you the help, like what's the argument? It gives you the help page for geom point. And you can see what are the arguments to that. X and Y are bolded, so these are the required parameters to use. And then there's also other parameters you can see. Alpha is more like density, color, fill, and so on. And then also we have a mapping that we would do that what column goes with, is it X or is it Y, and so on. So here, we got our data. So we say ggplot data, and then we know what geometry we want because we want a scatter plot. And so the X, we're using the population. Since it was in millions and wanted to have it would be easier to just divide it by millions and then add a label essentially. So we divide the population by million, and then the Y is the number of murders. So this was just like 2 lines, and you get a quick plot of the murder rate based on the population, the number of murders based on the population. So if you want to actually add now a label to it to know which state have what's the number of murders for that state, you can add a label as I've done here. You just add, now you add another layer. So this is geom text to add the labels. And again, you have this mapping, basically says, what's your X, what is the Y, and then the label. As you can see that you don't have to put the X and Y because these are required and assume the first and second parameter. You can actually just drop the X and Y and just pass it in. And then here you have the label. But as you can see, this puts it exactly where the dot was because it's the same location we're telling it the X and Y location. So then we can add nudge. So it basically moves it a little bit so you can see what point goes with what label. Another thing you can do, I don't know if you noticed in these ones, we both had the mapping both in the geom point and geom text. So if you just want to define it once, you can have it globally defined inside of the ggplot, and instead of keep repeating it for each layer that you add. However, you can add more for each layer. The the specific properties for that function, you can add it. But also if you want to change something, you want to plot some other point here, you can add it here. So the local one will override the global one that you have here. You can also assign it to a variable. So here I've assigned this little ggplot to p, so I keep using this p variable instead of repeating this in the next slides. Also, we can scale it. So there's different transformations that we can use if you need to transform your x and y data points. So here we want to do log 10. And if you look at the cheat sheet, you can see there's different transformation that are available by default in ggplot, and log 10 is one of them. So you can do the scale your x and then also scale your y. There's also, because this transformation is so common, there is also specific functions that you can use. So this is the same thing, it's just a different way of calling it. To scale x log 10 and scale y log 10. Then if you want to add a title, you just add a title. So you see, keep adding, you can keep adding by different layers by adding plus sign and then just saying what you want to add to create a new layer. And then you can add a color to the points. Here I'm just saying color purple, so it just colors all of my points purple. So just a revisit to actual plot that we were trying to plot, see, okay, what else do we need here? So we see there's like kind of like a different background color, and then also the regions are different, color coded differently based on the region. And we see that we have this variable in our data set. So then we can essentially, instead of saying, okay, color code everything purple, color code it based on the region that we have. And then now you see the color coded differently. And then we also, and it automatically gives you a legend for the regions. So, and the original plot also had a line fit. So here is just some code to create that line fit because we needed the murder rate. So we calculated here, and we also added basically geom AB line. So with the AB line, you pass in the intercept and slope, and then the parameters to that line. And here also I've used another package, ggRipple, that is also for similar to the nudge thing that we did to move the labels here, like a little bit to the right or left. And also here I've added the scale color district. So for the legend, we will use a capital R to be nicer. So this is so if you want to change your legend. So now here we have this line that we added. So this was like another layer that we added essentially to our plot. And also one last thing is the theme. So that plot was used by the economist theme. So there's different themes available. By default, ggplot has a couple of themes, but if you want a specific theme, so some of the journals have their own, and in other like packages that have it. So these GG themes have some useful themes that is nice that you can use. So then we just changed our theme to be Theme Economist, which is from the Economist magazine. And here now we have our pod. So we're back to what we started and we were trying to show. But essentially, it's very quick. So if you just want to have X and Y, you can just say you just geom point and plot it, and you can keep adding to it or change the size of the text and all this stuff. So you can look at, again, I suggest the ggplot cheat sheet. It's very quick to see, but mainly you want that you need the data and then a geom object, and then geom text and so on that you can just keep adding to it. So I wanted to talk a little bit about some of the studies that I'm currently doing and show some of the analysis that I'm doing to study depression. And so our study The protocol we're on is characterization treatment of depression. It's more specifically adolescent depression. And it involves a lot of interviews and questionnaire, and we have healthy volunteers and subjects with major depressive disorders. And we assess behavioral changes using interviews and questionnaire. We also do a lot of imaging. However, due to COVID, we paused that for now. And then also we collect blood samples. And that also has been paused because we are not bringing subjects to the campus yet. But essentially, we have a lot of data through questionnaires. Here is a plot of for our referrals. So we usually send out postcards. So each line here shows a set of postcards that was sent out. And it's crazy when I looked at these numbers, it's like 180,000 postcards. So this shows when the postcards were sent out, and the study's been going for a couple of years. So on the x-axis is like every couple of weeks that we're showing. And we're also color coding by if it's HV or MDD. And each point is the number of referrals that we got for that week. So you can see right after we send the postcards, we get a lot of referrals, but then it drops quickly, and then you see it kind of going up and down. And this one was sent after COVID, and these are first they are before. And you can see that we still got a good turnaround, and people wanted to participate in this study. So this is just one visualization that we use usually in our weekly meetings to kind of see how many subjects are coming, how many referrals we've had. Just a quick look at the data we have. And sometimes just putting the data in a table is fine. It's good. It's actually, you can look up numbers. So tables are good if you want to do like a quick lookup, and then graphs and plots are usually good if you want to see patterns. So we tend to have more females than male, and we have more NDDs than HB. So overall, we have 194 data sets here. And like I said, and then this is a longitudinal study. So when subjects enroll in our study, they used to come in every 4 months. Now it's all via Zoom, but we have multiple visits during the year. So we have followed them longitudinally. So we have data for them both before COVID and after COVID. So here I'm using, I'm showing the scores from MFQ, which is a mood and feeling questionnaire. And you can see on the left is for the healthy volunteers, and then on the right is for the MDD group. And I've separated them by year 2019 to 2020. So a year before COVID and a year after, and also by season. So you can see for the healthy volunteers, they tend to be pretty low overall. The average might be slightly higher for the year 2020. However, if you look at the MDD group, you see that they tend to be lower. So for 2020, which is the year we had COVID had started, it seems like that they have a slight decrease. And I should say higher scores are worse. So this is kind of an interesting results we got. Again, this is ongoing work. So I'm just showing some of the plots that we use for the analysis. And here, so just going over the code a little bit. This is using another package dplyr. So this one just says typing this data and using this data and filter it by HV. So this produces the plot on the left. And if I wanted for the MDD, I basically change this to MDD. And then once we have our data, then we can do the mapping. So here we say the X is the seasons that we have. It's essentially season in the year. And then Y, we're plotting the MFQ scores. And then the fill, so I'm saying to fill the box plots with the year. So we're color coding it based on the year. And then here's essentially what we define what type of plot we want. And I wanted the box plot. So that's, so these 3 lines basically to get the box plots. And the rest of it is essentially saying what are the labels you can see here. So the X, I didn't want to add another label. And then the Y is, this is defined elsewhere, basically saying self-FMHQ. And also like you can see the angle, these text the tick marks essentially are angled, so that's where you define it. So there's all these like different properties and parameters that you can add to your plot. So it gives you a lot of flexibility. So by default, I think it gives you a good starting point, and you have a lot of, you can get to see things very quickly. But then if you want to have a nicer plot for publication, then you have a lot of parameters and settings that you can modify. And then here, I'm just showing all the data we have from a year before and a year after for MFQ, which is a measure of depression. And you can see sometimes data is not as clean as you hope or you want, and it's just variability that we have in our data. So each line here shows each individual subject over time. So you can see so one subject from here to here. So, and each subject has different time points because sometimes they may miss their visit or something. And then the red shows the healthy volunteers, which you see it's mostly down here. And then the MDDs obviously have a higher depression score. And this line that I've added here is when essentially who declared COVID as a pandemic. And you can see that we don't see really any clear pattern. I mean, and sometimes on top of you plot your data, you don't see anything or what you thought you would wanted to see. So you don't see any specific pattern over time between a year before pandemic and a year after. Also, as I mentioned, it's very important to look at the data and for outliers. So here I'm plotting I average everybody, like each subject score for 2019 and each subject score for 2020. And they're just, so the lines are connected, those are the same person. So you can see there is this one subject that goes, so 26 actually is the maximum score you can get in this questionnaire, and it goes from 25 all the way to 0. So this was like a puzzling result because one is a healthy volunteer, so we don't expect such a high number here. So I asked, so we looked at the data and tried to figure out what's going on here. We still don't know what happened, why the person scored so high here, but we think it's actually error because we looked at multiple data points. All of his other points after this point is 0. Also the parent score, and that was 0 or 1, so really low. So I don't think this is a correct number. So, and we can like drop this one data point, at least one that time point that they had. And here you can see there's a slight increase for the healthy volunteers, but again, for major depressive disorder, subject with major depressive disorder, as you can see, there's a mix of up and down, but maybe even more down between before COVID and after COVID. So we also have, so like I mentioned, we have MFQ, and SCARED is another questionnaire that is related to anxiety that we've collected for a couple of years for these subjects. But once COVID started, we also started collecting crisis, which is the coronavirus impact survey. And so far, we actually had 8 waves that we've collected this data. So this is a type of visualization that one of my colleagues created to show kind of the spacing that it's kind of goes like some was mid-September, but then we didn't do anything until late January to try to space it out and show there is like at the beginning we collected a lot of data, but then we didn't collect as much. So we also have this nice data set that we collected a lot of these individuals that we have. And then for them before that, obviously we don't have the crisis measures, but we have different mixed questionnaires that we have. And this MFQ and SCARE we collect both before and after. So here is just showing sleep pattern during COVID. So the crisis questionnaire has a lot of questions about daily behaviors. So how many hours you sleep, how many hours you exercise, how much time you go outdoor, and so on. So we have a lot of data points to basically analyze and look at, which is actually quite challenging. You want to look at all of them, but Here is just showing sleep pattern during COVID-19. So you can see for healthy volunteers, it looks like you can see quite a pattern that the sleeping between 6 and 8 hours keeps increasing over time. And then I think so at the beginning of the COVID, maybe people slept more. And then now as things are getting back more to normal, it's going to more 6 to 8 hours. But the major depressive disorder subjects, you don't see this uh, as it's not a clear pattern. I mean, there's a little bit of changes here and there, but not quite as what we see with the sleeping and with the healthy volunteers. So this was used with the genome bar, and also with the genome bar, you can have it to show. So here they're all normalized to 1. So this would show the percentage essentially. So this is good if with each wave, because we didn't have the same number of responders. So we send it to about the same number of people, but we have variable, I guess, rate that we get the response back. So this was good to normalize it so you can compare it because it's as a percentage. And then there's different properties for the genome bar that you can set to have it to normalize to 1, or just essentially show the number of subjects that you have. So these are about 150 or so each round. So it would be different, but just made a note that you can, for the plots and for the genomes, you can set the properties differently and get different plots essentially. Also, another note is that, so this one is not very colorblind friendly. I showed it to a friend who's colorblind, and they said that this is really hard to differentiate between 6 and 8 hours to 8 and 10. So this is also something to keep in mind for publications. And this is I didn't find in ggplot the default option to just basically say use the colorblind friendly version of colors, but you can define, but there is like a palette that you can define that they suggest for that would be used, that would be more clear for people who are colorblind, and this was one of the options. So you can see there's more clear difference between the orange and blue. So I always think about that too. Something that I also forget sometimes because I just go with the default option. So this would be good to remember. Also, I wanted to show some imaging data because I've done a lot of work and I find it very interesting. So far we talked about data that we have set of data and we want to plot it, and I talked about the Cartesian coordinate, but with the imaging, brain imaging data, you can plot the data on the essentially the brain images itself, and there's different properties that you can display. So here I've shown, this was a study with the spastic paraplegic subjects compared to control. And here is from a diffusion tensor imaging. So the colors show it maps the direction of fiber tracks. So here the green is anterior posterior direction. The red, which is the corpus callosum connecting left and right. So it's mostly red or pinkish kind of, so you can see the blue. Here's posterior internal capsule, but cortical spinal tract goes through, so you can see it's blue, bluish color. So you can see, look at this image, and real quickly you can see what's the direction of the fiber tracks. So at each location, essentially you can also display this with the lines, so it will show different orientation. But here colors seem to show quickly, you can see what's the different orientation of different fiber tracks. Here is the just essentially average of the multiple brain MRI images. So this is how the images look like, what the T1 rated images look like in default. And then another encoding you can do is the size. So the density here, so the darker regions are areas that were smaller in the patient group, and the white are larger. So you can see the areas that are affected are displayed as dark regions. So you can use the density here to show. So at each location in the brain, it's like color coding, well, not color coding, but using the density, you can show the size. So here we're showing the orientation, and then we're showing the size. And you can see that there's very specific areas of the brain that are affected by this. And it's actually based on a mutation in the gene. So then another study that I was part of that I looked at is the Mobius syndrome subjects. So these group of subjects are essentially, they have problems. They cannot look laterally, and they have some facial paralysis. And there's a classic Mobius subject, but then there's also some people who have more problems with this disorder and have other phenotypes associated too also. So here, so it's kind of more zoomed in. So we found this one area that I've highlighted here that was very different between the healthy volunteers and this group of subjects that we looked at. So then we can look at each individual and plot it. So this value is for this one area. So you can see for brain images, if I want to look at for all of them, it would be like kind of crazy to look to plot all of this stuff. That's why we look at the brain images themselves to see patterns. And then we did the stats on this, and we found this location is very different. And we also used it for machine learning to train a classifier. So here is our training data. So this is the controls for that location. For one would be that the size didn't change essentially. And you can see some subjects have larger, that area is larger and sub-subject is smaller. And then here is for the classic Mobius, which is clearly much smaller than this healthy controls that we have. And we use this for the training. And as we got new subjects to join our study and we looked at it, you can see these are all Mobius subjects that we have here, that they're all like have the smaller, also have this region is smaller in these subjects. This is for subjects for a different disorder, which is similar to Mobius, but it's not. So you can see there's a clear boundary. So we essentially were able to find a biomarker. This one was misclassified, so this subject doesn't fall into that. So essentially was misclassified, but so you can see there's a clear difference. So we went from the looking at the brain images. You can, like I said, you can look at the colors that shows the different orientation of fiber tracks, or we can look at the volume changes, and then we can plot them and see if there's any differences, or use them for other analysis. So some of the references that I want to point out, as mentioned, this is some of the murder data set came from this group, and they have a lot of good examples using ggplot and R, and also different packages that you can, that is really good for data analysis. And then ggplot, which is part of the tidyverse package, so you can import tidyverse, which brings also has dplyr and other good libraries to work with the data. But since we were just using ggplot, I just showed the ggplot here. And there's also really good cheat sheets on R for quickly looking at the data and seeing what, getting the syntax correctly is very useful. We didn't talk about the interactive graphics, but here's a couple links. Like I said, it would probably involve more programming, but for quick data analysis, or to find out if you're doing something right, or just to see something really quickly, I think ggplot is very useful. I also recommend this book. Is an old book, but it's classic on visual display of quantitative information. And then this is our lab. So just want to highlight Peyton, who's one of the postdocs at the NIH that I worked with, that she helped with some of the slides. And that was it. So I know I went over quick, so I think that leaves a lot of time for questions. And thank you.
Thank you. Thank you, Neda. That was a really good overview of especially the sort of process that you use to kind of work through the exploratory data analysis and kind of look at your data in different views. So I have questions for you, but before we move to that, I want to remind everyone that if they have questions either about what was in Dr. Sadeghi's presentation, or I'm going to put her on the spot, if you just have general questions or advice about data visualization techniques that you've run into, please feel free to put those in the Q&A. section. For now, I want to go to a question that popped up while you were talking. And so this one was answered, or excuse me, asked by an anonymous attendee. So I will go ahead and ask it. And so this question was about the chart with the depression scores by the year between the two groups. And the question was, how did you get the final lines? So are those the mean scores of each participant at each time point? So
Is this the one?
yeah, why don't you tell us about that one, and then maybe the one where it's showing the difference between the years for each person, where you were looking for outliers.
Oh, different. Okay.
But you could tell us about both. How did you get
this
the lines for both?
I think this one is the one. Yeah, I used essentially to calculate the summary statistics. So I combined all the data points for that one subject and average them. So with the dplyr which is another package part of the tidyverse, is a good package to use to combine data points. So basically there's some filtering. So I basically filter it by group it by that subject and then average the data, the MFQs for that subject. I have for the actual plotting, I think I have the code here. But this averaging I did beforehand. So there's a summary data that I calculated. So again, if you look at the dplyr syntax, I mean, if that's specifically what the question is, but for the line, if you just have, here I have GM line, and because I have grouped it by STAN, so here is essentially the identifier for my subject. Because I have that as part of this mapping here. And then I said do a line, it knows to basically connect these two lines because it knows these two are from the same subject. And then this is also another good thing, facet grid. So I said parts here, this is my diagnosis variable. So it's the HV or MDD. So I'm basically saying do a HV MDD versus male, female. So that's why we get the 4 subplots that here we have. But essentially to get these lines, it's this grouping that I have in my data that I actually have it in this AES function, and then also adding this geom line that has it. But before that, I have to create this average column, which is essentially averaging all the values that I have for that individual subject.
Great. And let's see, I'm actually, so Elizabeth Israelowitz asked a question, but an anonymous attendee asked a very similar question. So Elizabeth, I'm gonna do the honors here, and I'm gonna summarize across these 2 questions, which are both about having multiple results. So the first question was about when you do a multiple regression, so you've got lots of predictors and you want to convey, the relevant information about all the predictors at once. And Elizabeth's question was about, when you have maybe a trial and you've got several different outcomes and you want to convey the effect of treatment on several different outcomes. So several similar things that you want to convey. Do you have tips for how to efficiently display those graphically?
So, I mean, I don't have it here, but this was something that I actually had looked at when I had the fitted line. Sorry, I don't have the fitted. This is just averaging across time, but I also have the linear models. That essentially the next thing I did was fitting a linear model, even though this looks like the data is all over the place. But and we had essentially straight lines, and this is I'm combining both male and female here. So one thing for the adding male and female, I could probably just do a separate line for male and female. And then if I had the regression lines, I could show it. So I could show the effect of male and female. But once you do that, if you have multiple covariates, you will have to fix each one to, for example, like the average value. For example, here we have age also. That could be one of the covariates, but we're not, I mean, this one I'm just plotting the average, but for the fitted lines, it would be, so I would have to fix the age. Let's say our average was 16 years old. So I fixed the age at 16, and then I show how the line would be for male group, for female group, and so on. So with the covariates, if you have multiple covariates, if you want to look at it, then you will have to, like, you will essentially have to fix one and show another one. But you can look at the relationship, I guess, between the covariates, or between the variables that you have at maybe correlation plots or something. But if you want to look at it, like in this case, we have over time data. It's we probably have to just fix one variable, look at the effect of one that is changing. And sometimes you can do two. Like I said, you can do time, and we can add gender. It won't be too bad. But then for age, we will have to fix it, and then we'll show the effect of age, and then add hold the gender fix or something. So usually we'll have to fix some of them to vary the other ones. And can you tell me what the latter one was, the latter question?
Yeah, so that was helpful for thinking about if you have multiple terms, and if you want to graphically show them adjusting for the other, that you have to basically reduce the dimensionality of your terms somehow. The other question was about if you're wanting to show multiple effects on different outcomes at the same time, how would you do that? And I would add to that, are there times where you graphically depict parameter estimates sometimes instead of the raw data themselves?
Yeah, I mean, if you, for example, here, you could have put essentially like a box plot that, if it was a box plot, yeah, that basically shows the range of the data instead of putting the raw data. I personally like the raw data just to see, because sometimes I feel like when we summarize the values, it makes it all look pretty, and then we forget how messy the actual data is. But definitely you can put essentially like here, and I'm connecting it, but you can put at each time point like a box plot of what's the variability at that time point, or you can add error bars. I don't have any to show here, but definitely you can add error bars to show how the values change over time. I'm looking to see if I have. This is one example. This is not error bars, but it's like a prediction interval that we've done. So this is a fit of to the early brain development data that I showed in one of the slides earlier. And this is the fitted line for this subject. It's actually a prediction interval based on other healthy volunteers we had, not healthy volunteers, other data sets we had. And essentially this point is the data point that we had, and this point is the data point we had. And the blue is the fitted line, but then the lighter blue is essentially showing the prediction interval. And this one is for the subject time point that we had not included to estimate this line, but afterward we plotted to see how well we predicted what the range would be for this value, and then we plotted it here. So definitely you can, instead of putting the raw data, you can put something like this that basically shows the average. It could be the confidence interval or prediction interval or the error that you would think. So your plot won't be as messy as some of the one that I showed.
Great. Shu-Ting, your hand is raised. I'm going to press allow to talk, so you can let us know if you want to say anything. You would need to unmute yourself, please.
Oh, hi, thank you. I was just wondering, like, when you do, like, say you do trajectory analysis and you have several subgroups that was derived from the trajectory analysis, and how you would plot the different trajectories across time. For example, like your depression slide, where you have healthy control and MDD groups, but what if there's like multiple trajectory lines within the group, and how would you represent in your plot?
Different, like, I mean, this is just 2 data points, but this is essentially, is that what you mean? There's like different, because here it's, I'm showing like healthy and MDD. Obviously this is just plotting it, averaging it. This is the like fitting it, but not fitting it to showing just 2 time points. Are you saying if there was different trajectories for different metrics you were saying, or different, I'm not quite following, like, wouldn't this do something that you wanted to do? I mean, here I know it's a very simplified example. I just mentioned. So are you saying if it was different kind of trajectory?
Right, like for example, like within MDD group, like say there are multiple lines that's derived from, because there's quite a range, right, for the group. So what if there's like one that's higher or one is lower, and what would be the best way to combine them on the same file?
I don't know if I mean, because I feel like if you, I mean, here, like I said, this is like an average, is not the fitted line, but if it was a fitted line, so then you would have one line that would be for MDD, and here is showing each, like then you would have a fitted line for each of the subjects essentially too. If you do a linear mixed effects model, so you will have a each line for each subject essentially. And then if it's different variables, you would have, I mean, different groups, you can just plot it. And I don't know if you're asking how, like, what's the best way visually to do it, or how syntax, like what the syntax would be.
I think combining with your slide 46 and 47, that helps. Basically, I think I can just do the lines based on the parameter estimates I generate and put them on the same graph.
Yeah. You will just like, because yeah, sorry, I don't have that example. I actually have a different presentation, but you essentially would do the fits based on, like I said, like here I have like showed the MDD and healthy volunteer, and if I do a fitted line, so then you basically fit the line based on the parameters you get from the model, and if it's for male or female, then it would be a different line that it will get added. You can add to the same plot. Essentially, you basically just add a layer that you can add that line, and then you can color code it differently to kind of show it's for a different one.
Thank you, that helps.
So we have another good process question from an anonymous attendee, which says, do you conduct your analyses and exploration in R, or do you just use R for the data display? Do you use other programs like Excel to clean your data?
So I use R for everything, essentially, for the cleaning part too. And for that, I would suggest the dplyr package, which is part of the Tidyverse. So I think if you look at the Tidyverse website, they have really good examples of how to go from like data cleaning to the analysis, to the modeling, to the visualization. So for each step of the way. And I find it easier because now I'm like more familiar with R to just stay in R rather than going between different data sets. But sometimes, I mean, it's been times that I've looked at, somebody has given me an Excel spreadsheet and I've looked at something because I was like quicker. I was just like, okay, I'm going to look, or just double checking that I didn't mess up something in my code in R to get the data. Like I can filter it in Excel to look at it, but I mainly stay in R for everything.
Great. And we have a question from Elizabeth Israelowitz, who should be able to talk now.
Yeah, so thank you, great presentation. And I was wondering if you had any suggestions regarding how to kind of discuss graphs that may show really unique results, but that maybe one of your outcome variables isn't significant. For example, running a multiple regression across ages using cross-sectional data, but age as a predictor isn't significant, but when you look through different groups, you see a lot of differences in the graphs that maybe the regression just isn't capturing.
So that's kind of tricky because, and I actually like we have different people in our lab that have different views on it because sometimes you see something in the graphs that are not statistically significant, and it could be for different reasons. And then if we try to show that, look, it is different, then it's, I think it's kind of like, because you don't want to, I mean, there is something that is showing in the graph that is kind of misleading because then it's like, it's not actually in, like when you do statistical analysis, sometimes the problem is because of too many variables in the model that is suppressing one. So I think it's good to do some analysis, or I guess find out why the stats is not showing what you're seeing in that plot. So and then also to make sure that the modeling is right. That would be important too. But I guess you were asking how to plot it if it's not significant.
Oh, no, I just like how to discuss it. And I think what you mentioned, you know, is important, just double checking everything and then kind of maybe having it be noted more as in the discussion.
Yeah, so I mean, I was in a lab previously that the stats kind of took a second, like, I mean, it was like, what do we see? And then if we would see it, then it's good and we put it out there. And then now in my current lab is like, okay, if we don't see it being significant, it goes to supplementary material. So I think there is like a balance in between. And if it's like something that you see and maybe it didn't reach significance or something, you can make a note of it and say it and have it, but also make it clear that it's not significant.
Thank you.
And I think one of the important things you're referring to, Neda, is the importance of showing the actual data points when you can in a graph, because the take-home message, especially for those of us in developmental disabilities, often we have really small data sets, and so the statistics might not capture everything.
Yeah, definitely, and that's a problem, because I think, and especially if you have a lot of variability, then that the stats may not show it, but something you will see in the data. And like I said, just looking at the raw data, because it helped us to find out that outlier, it just didn't make sense. That person was like a healthy volunteer and then goes from the highest possible score to the lowest possible score. So just looking at the raw data, I think it's very important.
So I wanted to ask a question kind of about process, because part of what we are doing here is kind of giving sort of tangible instructions, which you've given a lot of really good ones here. So when you are thinking about which plots you are going to use, what do you consider? Are you thinking about the data type that you have? Are you thinking about the specific type of hypothesis or the model that's going to be used? Like, how do you decide between the different types of plots that are available?
So, I mean, some, for example, like that I showed with the sleep one. So I would say for the category, if it's a category, so if you have a few categories, I would say this type of plot would be good, just because you can show different groups how it's like a category, basically in this group, how many people you have. So I think a bar plot would be good for that. But then if you have different data points, like, I mean, here we did, so a lot, so I'm sorry, I don't have didn't put guidelines here, but it depends on if your variables are continuous or is it discrete. And usually with the continuous, if you have, if your dependent variable is continuous, then usually we'll use a scatter plot. I think that's like the best way to go, unless you want to like summarize it, which I did for the for the MFQ scores. I wanted to group them, so then I did the box plot, and then also I wanted to put it in different, because I was trying to compare like seasons 1 year versus another year. So it would be harder to do a scatter plot. So it's a box plot comparing, and then you'd have the quantiles of each one. There's the median, is the percentile of the 25 percentile, 75 percentile. So I think it depends on the type of data you have, if it's continuous or categorical, and that tells you a lot which one to use. So like I said, if you were to just look at the raw data and they're continuous, I would, the scatter plot would be my to-go one. And then if you want to summarize them, I think box plots are a good one. And then for the categorical one, I would say a bar plot would be good.
And it sounds like having a good sense of what the question is that the plot is answering is helpful, because that sort of determines how you're like here, you know, how
Yeah,
you
definitely.
organize
I
it.
mean, I think at every step of the way, especially it's like the audience, you should have the audience in mind, and what you're trying to convey to them. Like, what are you trying to point out to them, and what do you want to show? That's very important to know what they would be interested in seeing, and are you showing that? And does the point come across? Like what you're trying to show? Like, for example, here, I kind of want to show that our data is all over the place. Like, we have a very high variability, and you can see it. And also, we don't see anything before and like any major, like something that you can capture with the eye. Like, you don't see any significant difference between before and after COVID, based on these plots at least.
So the idea of audience, I think, is really important with plots. And I wonder if you could speak a little to how you think about the different audience for a talk where you're using slides versus the audience that you have when you are preparing something for publication, versus, you know, another aspect you mentioned was just communication, maybe among investigators. So the audience that you have when you're preparing like the results of your EDA to share with your collaborators. How do you think about that when you're sort of choosing how to design your slides, or excuse me, your figures?
Yeah, so I think, especially for publications, I mean, a lot of times goes into like tweeting the, like tinker around and like trying to see, okay, make sure that, I mean, some of the things that I might not have been the best here too, it's like the labels on the plots, like just the text size and so on. Sometimes I'm not even super careful, like, because I just do it quickly and I use the default, and then you show it to the audience and they can't even read it. So I think the important thing is like make sure the labels are nicely labeled and the size is large enough to see it. And then another thing was the issue that I said with the colors, just make sure that your audience can actually see the colors. But I think yours was more general of how the audience, like I said, with the first plot that I showed, I really like that because I think it gives a story of what happened with the troops. And I think it was like a really nice visualization of showing it. But sometimes, depending on the audience, especially if they're more scientific, if they're more in your field versus they're not, like you can go more into the details of what, how you measure different things, what they are, and people, there's also expectation maybe in the field of what they're gonna expect. And I think keeping that in mind, so if the data is more surprising, so have it basically show it why that is the case, and have them notice, like be able to convey your message essentially of what they are trying, what they are looking for. And trying to give a specific example. Yeah, I think overall just making sure that if somebody else showed you that plot, does it make sense or not? I think even if somebody just like out of the blue is just like this. And then I think the other important thing is they should be like standalone. So to have all the information that is needed to have it on the plot, because sometimes like in presentations, people are paying attention, sometimes they're not, and then maybe they miss what you said. So have all the key points to be displayed and put on the plot. So all the main points that you want to get across, to have it as a label or legend or a title, have it all be there. But again, if it's somebody, like I said, if it's in your field versus not, or if it's familiar with the topic then you can go deeper into the data versus the more overview of it. So more of a big picture. So I think that's also important.
Great. So really considering the audience when you're making the plot. Okay, so thank you. That was awesome. If there are any more questions, we're still going to be on for a couple more minutes, so people should feel free to put those in the Q&A. But I wanted to leave enough time for Drew to give us a quick overview of the program that we have starting tomorrow, because Dr. Sadeghi's presentation was a really great segue into the broader conference. And so Drew's going to give us a quick overview of that, and then we will rejoin to ask any remaining questions and adjourn.
Great. Well, I want to first thank you, Dr. Sadeghi, for the great presentation, and you, Dr. Farmer, for moderating today. So we'll start tomorrow at 9:00 a.m. and that's Central Time Zone, with opening remarks from John Colombo and Rodney Samako and Eric Stork from Baylor. And then Nancy Brady will give a plenary talk, and then we'll have our first 9 symposia, and finally our first poster reception.
Well, I know we are definitely all looking forward to that. It's going to be different, but fun, hopefully. So Dr. Sadeghi, thank you so much for this. Oh, sorry, I don't know if you guys could hear my computer phone ringing there. So thank you so much for joining us and for sharing these tips for data visualization. This recording will be available on the conference website for those of you that joined a little late and didn't see that. Again, thank you, Dr. Sadeghi, and to the rest of you, we are so excited to see you at the big conference tomorrow morning.
Thank you for having me. Thanks, everybody.
Thank you.
Bye-bye.